generate an output. And if it generates an output, it better be one of these correct outputs. Right?
Massachusetts Institute of Technology algorithm lecture and Need for Speed Most Wanted. He's talking about inputs. This is a controller. Each button is an input that has an effect on the game.
An algorithm is a function. It takes inputs to outputs. Right? An algorithm is some kind of function, right, that takes these inputs, maps it to a single output, and that output better be correct based on our problem. Okay? So that's what our algorithm is. It solves the problem if it returns a correct output for every problem input that is in our domain. Okay? And the example for does anyone have a possible algorithm for checking whether any two of you have the same amount of time as specified before? I'm going to let someone else have a try. Sure. Great. So what your colleague just said is a great algorithm. So essentially what it's going to do is I'm going to put you guys in some order. Okay? I'm going to give each of you a number, 1 through however many number of students there are in this class, and I'm going to interview you one by one. Right? I'm going to say, what's your birthday? And then I'm going to write it down. Right? I'm going to put it in some kind of record. Okay? And then as I keep interviewing you, I'm going to find out your birthday. I'm going to check the record. I'm going to look through all the birthdays in the record. If I find a match, right? Then I return, yeah, I found a pair, and I can stop. Otherwise, if I get through the record list, I don't find a match, I just stick you at the end of the record. Right? I add you to the record, and then I move on to the next person. I keep doing this. Okay, so that's a proposed algorithm for this birthday problem. For birthday problem, what's the algorithm here? Maintain a record. Interview students in some order. And
I changed the video output not to HDMI converter, and now it looks much better.
Birthday in record. And if it is, return pair. So return pair. Otherwise, add new student to record.
I have to adjust the camera.
And if I go through everybody and I haven't found a match yet, I'm going to return that there is none. Right. Okay, so that's a statement of an algorithm. That's kind of the level of description that we'll be looking for you in the theory parts of this, theory questions that we ask you on your problem sets, right? It's a verbal description in words.
What button did I press? Did I press that button?
You don't know what to do, but if you said this algorithm to any of your friends in this class, right?
Am I pressing the wrong button?
What it is that you're doing. Yeah. Pure function, does an algorithm have to be a pure function in mathematical sense, as in it needs to map to a single output? So we're talking about kind of a functional programming definition of a function, right? This is, I am talking about the mathematical, I have a binary relation, and this thing has an output for every input, and
the controller is going haywire, I think.
That's the mathematical definition of function that I'm using for when I'm defining an output. Yeah. Yeah, an algorithm's a procedure that somehow I can do whatever I want, but I have to take one of these inputs and I have to produce an output, and at the end it better be correct. Right? So it's just a procedure. You can think of it as like a recipe. You can think of it as it's just some kind of procedure, right? It's a sequence of things that you should do, and then at the end you will return an output. Okay. So here's a possible algorithm.
Sequential sequence.
Okay. Now I've given you what I argue to you, or I'm asserting to you, is a solution to this problem, and maybe you guys
consecutive sequence.
Right. So how do I convince you that this is correct? Right. Well, if I had. If I was just running this algorithm on, say, the 4 students in the front row here, right, I could argue it pretty well to you. I could go through I could assign these 4 people birthdays in various combinations of either none of them have the same birthday, some 2 of them have the same birthday. I could try all possibilities, and I could go through lots of different possibilities. I could just check that this algorithm returns the right answer in all such cases, right? But when I have, 300 of you, that's going to be a little bit more difficult to argue. So if I want to argue something is correct in mathematics, I want to prove something to you for some large value, what kind of technique do I use to prove such things? Yeah, induction, right? And in general, what we do in this class
have to adjust the camera.
Is we write a constant size piece of code, right, that can take on any arbitrarily large size input, right? If the input can be arbitrarily large but our code is small, then that code needs to loop or recurse or repeat some of these lines of code in order to just read that output, right? And so that's another way you can arrive at this conclusion that we're going to probably need to use recursion, induction, and that's part of the reason why we asked you to take a course on proofs and inductive reasoning and discrete mathematics before this class. Okay, so how do we prove that this thing is correct?
I don't know what button I'm pressing that keeps showing that.
We gotta use induction, so how can we set up this induction? What do I need for an inductive proof? Sure. Base case, we need a base case. We need some kind of a predicate, but we need some kind of statement of a hypothesis of something that should be maintained, right? And then we need to have an inductive step, which basically says I take a small value of this thing, I use the inductive hypothesis, and I argue it for a larger value of my well-ordered set that I'm inducting, right? Okay, so for this algorithm, if we're going to try to prove correctness, what I'm going to do is what do I want to prove for this thing? That at the end of interviewing all of you, that my algorithm has either it has returned with a pair that match, or if we're in a case where there wasn't a match, wasn't a pair somewhere in my set, they return a match, right? That would be correct, right? So how can I generalize that concept to make it something I can induct on, right? What I'm going to do is I'm going to say, let's say after I've interviewed the first K students, right? If there was a match in those first K students, I want to be sure that I will return a pair, right? Because if after I interview all of you, I've maintained that property, then I'll be sure at the end of the process I will have returned a pair from exists. So here's going to be my...
The controller has been removed? I'm having, the controller's haywire. It's the only one I have.
First K students contain a match. Algorithm returns a match before interviewing, say, student K plus 1. Okay, so that's going to be my inductive hypothesis. Now, if there's n students in this class, right, and at the end of my thing, I'm trying to interview student n plus 1, oh, student n plus 1's not there. If I've maintained this, then if I replace K with n, then I will have returned a match before interviewing the last student, or when I have no more students left. And then this algorithm returns none, as it should, right? Okay, so this inductive hypothesis sets up a nice variable to induct on, right? This K I can have increasing up to n, starting at some base case. So what's my base case here? My base case is the easiest thing I can do, sure. 2, that's an easy thing I can do. I can check those possibilities, but there's an even easier base case, yeah. There's an even easier base case than 1. 0, right? After interviewing 0 students, I haven't done any work, right? Certainly the first 0 can't have a match, right? And so this predicate, this inductive hypothesis, is true just because this initial predicate is false, right? So I can say, base case 0, check, definitely this predicate holds for that. Okay. Now we get to go for the meat of this thing, right? Assume the inductive hypothesis true for K equals, say, some K prime.
I think I'm going to put in a new game.
K prime plus 1, right? Then we have 2 cases. One of the nice things about induction is that it isolates our problem to not consider everything all at once, but break it down into a smaller interface so I can do less work in each step, right? So there are 2 cases.
Oh, I knew that was about to happen.
Either the first K...
Yeah, the controller's just going haywire.
Right? In which case, by our inductive hypothesis, we've already returned the predicate, right?
I'm going to put in a new game.
It doesn't have a match in the interview, the K plus 1 student, the K prime plus 1 student. If there is a match in the first K prime plus 1,